Welcome to EDU World Space.
Here's the problem 23.20. In this question, the most important oxides of iron are the magnetite, which is Fe3O4, and the hematite, that is the Fe2O3. All right, question A is asking you to calculate the oxidation states of iron in this compound. So for the first one, magnetite, since it's a neutral molecule, the oxidation state of iron and oxygen cancel out each other. So the sum of the charge of iron and oxygen should be 0. And we know that the oxidation state of oxygen is equal to -2. And we assume that the oxidation state of this iron here is equal to X. So we have the following equation: 3X plus 4 times -2 equal to the total charge, which is 0. And solving this equation, we get the number X equal to 8 divided by 3, that is approximately 2.66. So we get a fractional number. This represents the average oxidation state of the iron, not for each one. So this is because by observing the crystal lattice structure of this magnetite molecule, it can be seen that 2 iron atoms are surrounded by a certain number of oxygen atoms and has a charge of +3. And 1 iron atom is surrounded by a different number of oxygen atoms, and that will have a +2 charge. So to represent the general oxidation state of iron in this molecule, we will use the average number 2.66. So the second one, since it's also a neutral molecule, the oxidation state of iron and oxygen will also cancel out. And we know that oxygen is equal to -2. And this iron here, we assume that the charge is Y. So we have 2Y plus 3 times -2 equal to the total charge, which is 0. So we get the number Y equal to +3. So the oxidation of the iron atom in the second molecule is equal to +3. All right, so now we look at question B. B is asking one of these iron oxides is ferrimagnetic. So explain your answer. So now we want to look at the crystal structure right here. This is for Fe3O4. This is a ferrimagnetic substance. It can be explained by the crystal lattice structure proposed by Neal right here. With the special spine structure, the large atom of oxygen ions are close packed in a cubic arrangement, while the smaller ions are represented in the gaps, and the gaps occur as 2 geometrical sides right here. So the tetrahedral, this one, the tetrahedral side, the iron is surrounded by 4 oxygen atom, and the octahedral side, the iron is surrounded by 6 oxygen atom. So it is showing that the tetrahedral and octahedral sides from the 2 magnetic sublattices A and B respectively. So this is A, this one is A, this one is B. So the spin on A sublattice are anti-parallel to those on the B sublattice. So the structural formula for the magnetite, we can write it this way: Fe3 plus times A Fe3 plus Fe2 plus BO4. So this kind of arrangement with negative AB exchange interactions possible between the two iron ions, and within the sublattice, the net magnetic moment of magnetite is due to the B side of iron 2 plus. So this is 2 plus, this is 3 plus. So the number of magnetic sides aligned in one direction being more than number of the magnetic sides aligned in the opposite direction. This magnetite Fe3O4 is very magnetic.